Hello and welcome to 7 Basic Quality Control Tools. This session is used to understand the basic 7 quality tools and how to use it in a real case study. These tools developed by Mr. Kaoru Ishikawa, and he claimed that these tools can solve more than 90% of quality issues. These tools are powerful, and using them the correct way and the correct order will lead, of course, to fix our quality issues. So first is the flowchart. Flowchart is a simple way telling us how the process is going and how the process should go. Process chart has dedicated samples for it. We will not go deep in each method, it's just an overview. But the flowchart shows where the process starts, where the process ends, where we can loop. So we know how the process should go, and we know how the process actually runs. So we know the bottlenecks, we know the non-value added steps, and we know the defect generation stages. So now I can understand my process. Then I go to the check sheet. Check sheet is a structured, reliable way so I can collect data. Check sheet must be combined with metadata. Metadata is who, when, and where. It's a simple, reliable way to create a data set to start my investigation. Then I have the data. Then let's prioritize the most significant problems using Pareto chart developed by Vilfredo Pareto. This chart here shows how many defects per each problem, and this line here is a cumulative line of the percentage of the defects. For example, the control PCB creates more than 60 defects, which are about 40%. And then with the heater element, about 60% of the percentage of defects. So using the Pareto chart, we prioritize the problems that I must dig in. For example, if I have time to fix only 2 issues or 3 issues, what are the issues that I must address? Pareto chart is a good way to tell us what is the vital few. The vital few are the few problems that create major problems. And we determine the trivial many, the many problems that create less defects. So, I know my process, I have the data, I know the problems that I must dig in. So, let's dive deep in each problem to know the causes of it using the cause-effect diagram. The cause-effect diagram or fishbone diagram or Ishikawa diagram. This diagram is used to list all potential root causes for each problem. There are common major categories like man, machine, method, environment, and so on, and I can adjust it to my industry. So here I have many branches, and with each branch I see the possible causes. So the use of cause-effect diagram is to list all potential root causes. After that, I take one problem, for example, to study it further, to know the correlation using the scatter diagram. Scatter diagram is used to know the correlation between the multiple variables. For example, the humidity and PCB failures. It can be positive correlation, the higher humidity, the higher defect rate. It can be negative correlation, the higher humidity, the less defect rate. It can have no correlation, no clear correlation between them. So the output of the scatter diagram, I know for sure, is there a correlation between the variables or not? Then I go to the histogram. Histogram is used to know the variation and to detect the trends. For example, these are the days of the week and these are the number of defects. I can have in a specific day high number of defects, and maybe there is a trend, and maybe they are depreciating over week, maybe they are ascending over week, maybe they are almost stable along the week. Know that failure doesn't happen because of a single error. It happens because of a trend, and histogram is a very powerful way to know the trends. Then the control chart. The control chart, after I know my process, I set my upper and lower control limit. I know what are the mean values. So now I can track my process. So I know each day where am I. Sometimes I go below my lower control limit. Sometimes I go above my upper control limit. Note that control limits are not specification limits. Now let's go to summarize how to work in the investigation process. First, using the flow chart, I understand the process. Check sheets to collect data, Pareto chart to know what are the most important problems to work on, cause-effect diagram to list all potential root causes, scatter plot to verify correlations and relationships between variables, histogram to know the trends and variation, control chart to control my process. Now we have an enjoying part, a case study. A case study for a pump shaft failure. Please note that all the data in this study is generated and assumed. They are not related to a real ESP failure, and this scenario is not showing a real ESP failure, but it is used to demonstrate how to use the QC tools. So, first of all, I use the flow chart to know the pump process flow. Using the pump process flow, now I understand my process. Now I can see where is the possible failure stages. Then I go to data collection using the check sheets. Now I have structured, reliable data to dig in. And using the failure mode prioritization with the Pareto principle, I know that the pump stock condition with the low end play are responsible for about 75% of the failures. So if I have time to fix only 2 problems, I will fix these 2. Then I use the fishbone diagram to know the possible root causes for each problem. And then I validate my assumptions and I find the correlations between, for example, the end play and the number of failures. In our case, I see a clear negative correlation. The higher end play, the lower defect rate. And then I made a study for the end play measurement distribution. So I see that most of my end play lies here between 0.01 and 0.02. And I see that there are many pumps below 0.01, which is critical. This indicates that I have a problem. And finally, I create the end play process control. So I know my mean value and I know how my value varies to know is my process sustainable or not, and I know when I should ring a bell because the end play goes below lower control limit or above upper control limit. And then after this, I made a plan for the corrective action until I have the result: improved pump reliability and reduced shaft failure. Thank you for listening.